Hello Year 11 and welcome to our walking talking mock where we're going to go through the foundation paper of the combined C2 chemistry paper 2. Now before we get to the questions I would like to point out that all of you will have access to a periodic table when you come to doing your assessments that looks like this. Please make sure that you use it throughout your test. It is loose, so just take it out and put it on the table in front of you. It's got all of the elements, it's got the groups. They're not labelled groups, but these columns here are the groups, so 1 up to 0, and then obviously you have the rows which we call periods. They are not numbered, so something you might want to do when you first get into the hall is just number those periods. That will particularly help you in the chemistry paper 1 exam. Always do it from the right hand side because the first period is actually hydrogen and helium, and quite often if people are numbering it on this side they start with lithium as number 1, but lithium is actually in period 2. You've got a key here, and this tells you what the numbers are about. So it tells you where the atomic mass is, which is the top number on this periodic table, and the atomic or proton number, which is at the bottom. So this is in your papers for a reason. Please make sure you use it. So we're going to start with question number 1. You'll notice that it's got 1 and the parts will be a dot, so 1.1 is the first question. So this question is about gases. Draw one line from each substance to the description of the substance, and it's worth 3 marks. So we know that we're going to have to do 3 lines, and there's going to be 3 things, so that means there's 1 line per substance. So we can go through, just always have a quick read of all of the words before we even begin. Don't just panic and try and get the line in, just take a breath, read through all of the information it gives you. So we're starting off with air, so the air that you breathe. So there's carbon dioxide in there, oxygen in there, nitrogen in there, but they're not bonded together. So that means that air must be a mixture. Okay, really important to remember, mixture is 2 or more different elements or compounds not bonded together. Okay, so there is carbon dioxide in air, there is oxygen in there, but the carbon dioxide and the oxygen aren't bonded together. So next one, we've got carbon dioxide. So we all should know that carbon dioxide is CO2, so it contains more than one element, and we know from our bonding in paper 1 that they are bonded together. So that means it must be a compound. Okay, so a compound is 2 or more elements that are bonded together. So we're left with 3 more options now. We've got element, hydrocarbon and metal. So our last one is oxygen. So we know that oxygen isn't a metal because it is on the wrong side of the periodic table. We know that oxygen is not a hydrocarbon because we did crude oil. We know that hydrocarbons contain hydrogen and carbon only. That contains neither. So it must be an element. Okay, and an element contains only one type of atom. So if it only contains one element, one thing, one atom, then it is an element. Okay, so that was out of 3. You get 1 mark for each correct line. So next one, 1.2. What is used to test for each of the gases? This is our gas test in chemical analysis, and they've given us two gases, carbon dioxide and oxygen, and then we've got what we use to test them. So we've got a glowing splint, so that's one that is blown out. We've got a lighted splint, so one that is already on fire. We've got lime water, which is that liquid, and we've got litmus paper. So which one of those is for carbon dioxide? It is draw one line, so it's only one thing, and hopefully we've drawn our line to lime water. So lime water is what we use to test for carbon dioxide, and it causes the lime water to go cloudy. So if they're asking for a positive result as well, lime water goes cloudy. Okay, so now we're going to do the test for oxygen. Now litmus paper, hopefully we know that damp litmus paper we use to test for chlorine. So it's not that one. Okay, and I keep saying, but I'll say it again, please feel free to annotate. They're only going to do the mark the lines. Lime water we've already done. A lit splint, that's going to be for hydrogen, and then it goes pop. Litmus paper is bleached. For hydrogen it's a lit splint and it pops. So oxygen is the glowing splint, and it causes it to relight. So if we were doing the positive test, it would be that it relights. So if you got one of those lines correct, that will obviously be 1 mark. Both lines 2 marks. Okay, next one, 1.3. Give 2 reasons, and it's worth 2 marks, so please make sure you give 2, and it says tick 2 boxes, but the amount of times that people will tick just 1 because they presume it's 1, please read it carefully. Give 2 reasons why the percentage of carbon dioxide in the air has decreased in the last 2.7 billion years. So this is looking at the change in atmosphere. So we're looking at why the percentage of carbon dioxide has decreased. So what would cause carbon dioxide to go down? So combustion, that's burning things, and that produces carbon dioxide. So it's definitely not going to be that. Dissolved in the oceans. So that is one of the ones we learnt about, that a lot of carbon dioxide dissolves in the oceans. Intense volcanic activity, that will produce carbon dioxide. So again, that one is producing carbon dioxide, so it's not that. Photosynthesis. Photosynthesis produces oxygen. It uses carbon dioxide, so that will cause it to reduce. And respiration, we know from biology, produces carbon dioxide. So all of these 3 produce carbon dioxide, so it can't be those. Or you might have remembered that it is those 2 that did it. So you get 1 mark for each correct box. Okay, next question. Oxygen reacts with sulfur dioxide. The reaction is reversible. What is the symbol for a reversible reaction? So do be careful on some of these questions. This is kind of an example of one. It's giving you some information here, but neither of those 2 sentences is actually needed to answer this first question. So do be aware of that, and make sure, I know that this one's a quite straightforward one, but sometimes they then ask a completely random question and people get confused. So make sure you very carefully read the question. It's only worth 1 mark, so it's only going to be a simple thing that you have to do, and in this case it's just going to be regurgitating that symbol. Okay, so this is the symbol that we need to make sure that we put. It can be as unneat as mine, they would still allow it. If I was doing a little bit neater, it would be like that. Either way, it doesn't matter, but we need these half arrows where half an arrow is pointing one way and half an arrow is pointing the other. So well done if you remembered that. 1.5, complete the sentence. In a reversible reaction, the forwards reaction is exothermic, So the reverse reaction is, and hopefully we know that if one is exo, the other has to be endothermic. Okay, now this one, a lot of people often ask about whether spelling is important. On these kind of ones, we're using key sort of scientific words that you wouldn't normally use in other lessons, like exothermic, endothermic. Please make sure you go back and check your spelling, because this one does need to be spelt correctly. Right, last one of question 1. A reversible reaction happens in apparatus which stops the escape of reactants and products. Equilibrium is reached when the forwards and reverse reactions, so reverse just backwards, reactions happen at exactly the same, and there is one ideal word, which would be rate. Remember, this whole chapter was about rate of reaction, would be rate. However, in the mark scheme they did allow speed or velocity. Okay, but rate is the preferred answer. So total up, how many marks you got out of 10? These questions were about reversible reactions and the chemistry of the atmosphere and chemical analysis. Okay, so moving on to question 2 now. Number 2, concrete contains cement, water, sand and small stones. 2.1. Concrete is a mixture designed as a useful product. What do we call a mixture that has been designed as a useful product? So again, it's giving you all this information here that you do not need to use for the question. This is the question. What is a mixture designed for a useful product? Hopefully remember from our lessons that it is a formulation. Okay, it's got a formula to it. So finite, that means that it's going to run out. It's not formula on its own, even though it does have a formula. And it's not a fraction, that would be to do with crude oil. So it said tick one box, it's worth 1 mark, so we only had to do 1. And if you got that correct, that's your mark. 2.2. Concrete contains cement. Cement is made by heating a mixture containing silicon dioxide. So it gives you a formula here. Why does silicon dioxide have a very high melting point? Tick 2 boxes. So again, another one where we have to tick 2. It's worth 2 marks. Obviously, we're going to get a mark for each box. And this question is actually from the C1, the paper 1 chemistry, which is to do with bonding. So do be aware that you are going to have questions from paper 1 that might pop up in 2 before they introduce the paper 2 content questions. So we have got the following list. It has a giant structure, is a simple molecular structure, it has strong covalent bonds, it has strong ionic bonds, it has weak intermolecular forces. So first of all, we need to think silicon oxide, dioxide. Both of those are non-metals, so the bonding that's happening in that is covalent. Ionic bonding happens between a metal and a non-metal, so it's not that one. Weak intermolecular forces would make it have a very low melting point, very easy to get it to change states, so it's not going to be that one. It has a simple molecular structure, so this is things like water, H2O, or methane, or carbon dioxide. Those two are going to be gas at room temperature. They've got very low boiling and melting points, so it's not going to be that one. So very well done if you ticked it has a giant structure and it has strong covalent bonds. I would hope that most people got covalent, knowing that is between 2 non-metals. Okay, next question. We've got a how science works question. So student A investigated how the mass of the small stones in concrete affects the strength of a concrete beam. All other variables are kept the same, control variables. The student added weights until the concrete beam broke. So they're adding a weight at a time, and they are seeing at what point the concrete beam breaks. Draw one line from each type of variable to the correct example of the variables. So in this investigation, it's worth 2 marks. So we need one line going from control and one from independent. So control variables, those are ones we have to keep the same. So looking at the picture, what would be important to keep the same so that it doesn't affect our results? So out of our options, we've got the length of the concrete beam, the mass of small stones in concrete, time taken to add the weights, or weight needed to break the concrete beam. So hopefully we realise that if we had a really long concrete bar, then that would break a lot more easily, so that would affect our results compared to if it's a very short one, which would be a lot stronger. So it's going to be the length of the concrete beam. Okay. Next one, the independent. So this is what they're changing. So what is being changed each time? And it says in here at the top, investigated how the mass of the small stones in concrete affects the strength of the concrete beam. So they're changing the mass of the small stones. So that one is going to go to here. The other variable that they might ask you about is the dependent variable, which is what you are measuring. And they are measuring when the concrete beam breaks, how much weight is being added to it. So if it was asking about the dependent, then this one is the dependent variable. The time taken to add the weights is not going to have an effect. Okay, so moving on, we're still with how science works, and this is going to start moving into the maths part of it as well, looking at graphs. So we've got a set of results here, so the mass of the small stones, and then the amount of weight needed to break the concrete beam. So the first part, very common question. Please, you will pretty much guarantee to have a drawing the graph question in your C2 paper. If not from something like this, then definitely for rates of reaction. So 2.4, plot the data from table 1. The first 3 points are plotted for you. How generous. Draw the line of best fit. And if any of you do not know yet that in science the line of best fit can be straight lines or it could be a curve, please make sure you remember that, because you can already see that this is starting to turn into a curve. So we've got the first 3 done for us, so it's done 1500. So our next one is 2000. Please make sure that you have got a pencil in your exam, just because it's very easy to make a mistake and you can't rub out pen, and then it's very hard for the examiner to see where you meant to put your cross. So we're now on 2000, so we're looking at 100. So on this one, 2000, 50, 100. And notice how the center of my cross, where they cross over each other, that's where the point is. Okay, do not put hearts or dots or anything like that. It needs to be a nice cross with the middle of the cross where you want it to be pointing at. The next one, 2250, is 85. So now I need to have a look at my scale. It's getting a little bit trickier. So this is 2500. So 2250 is going to be halfway between these. So it's going to be here. Okay, 2 little boxes and a half. And I need to go up to 85. So again, trickier with the scale. So here is 50. that is 100, so every 2 boxes must be 10. So that's 60, that's 70, that's 80, so this must be 85. Now a little tip on this one was easy to do, this first one, so you can already see the pattern that is happening. So if your next crosses are completely off that, then you might want to just double check it. So the next one is 2565, so this is 2500. I realise, and this is why it's so important to use a pencil, because even the best of us can make a mistake. So I plotted that on the 2500. Please take a rubber to your exam as well, whereas it needed to be on the 2500, so that one should be there. Right, 2565, so 50, 65 is there. And then the last one is 2750 and 35. So 2750 is here. And then we need to go to 35. So 10, 20, 35. Okay. Now on the mark scheme, if you have got all of your crosses plotted correctly, so that they are in the same place, you're allowed to go off by half of a small square, so you do need to try and be pretty accurate where you're putting them. If you've got all of those crosses, then that's worth 2 marks. Okay, drawing the line of best fit is normally worth 1. So even if you don't do the line correctly, you're still picking up most of the marks. So the next thing I need to do is my line of best fit. And as I've said in previous ones, I've turned my paper upside down. I like to pivot on my palm here. So I put that in there and use that to go round. So I just continue the line, going through them. It doesn't matter if you continue a little bit more. What you will be marked on is the line between here and here. So if you included that, that will be your 3rd mark. Right, 2.5. What mass of small stones would be needed to make the strongest concrete? Give a reason for your answer. So we need to have a look at our graph. The one that can hold the most weight is going to be the strongest. So our strongest one is here, which was 1,500. So if you put 1,500, then that is a mark. The reason, so now you need to say why you've picked 1,500. And you could put, it was the top of the curve, you could say the highest point on graph. So what is the reason why we chose 1,500? So you get 1 mark for this bit and 1 mark for this bit. Okay, last bit of question 2. Student B did a similar investigation. Figure 3 shows student B's results. So we're going up, got a nice curve here. How could student B improve their investigation? So it's a similar investigation, but their line looks different to ours, because our line then started to go down, but their one's just going to keep going up. So if I was looking at this that somebody else has done, I would say that if you keep adding bigger mass of small stones, it's just going to get stronger and stronger and stronger. But we know from ours that it doesn't. Now it's only worth 1 mark, so you just need to say something very simple about getting more readings or more results, or take more measurements. Okay, they'll also accept, do the test with bigger masses of stones, anything like that, something indicating that we don't know what's going to happen here. So total that up, it's out of 11, give yourself a mark and make a note of anything that you were unsure of. Right, so we're moving now on to question number 3. A student investigated the rate of reaction between magnesium and hydrochloric acid, and here we've got the apparatus that the student used. So we should be familiar with this from the lessons. Here we've got our gas syringe giving us a much more accurate reading. We've got our acid and our magnesium in the conical flask. First bit is balancing a symbol equation. Now this is worth 1 mark. And it's got an underlined bit here. That is where we need to put our number. So we know that this is going to be the only thing that we have to balance. So you want to look at how much we have of each element. So here is 1 magnesium. Over this side there is 1 magnesium. So the magnesiums are balanced. Here we've got 1 hydrochloric acid. So if there isn't a number next to it, it just means there's 1 of them. So 1 hydrochloric acid, so that's 1 hydrogen here, but over here we've got 2 hydrogens. So I need to get another hydrogen on this side, and the only thing you can do is put these numbers in front of the symbols. So if we put a 2 here, 2 times 1 is 2, so I've now got 2 hydrogens on this side, 2 hydrogens on this side. So the last one to look at is chlorine. So now that I've added this 2, I've also got 2 chlorines, and on this side there's 2 chlorines, so that is balanced. So well done if you got that. That is worth 1 mark. I would suggest if you have got a balancing symbol equation, you're not confident with it, then leave it. Don't spend a long time on it, because each mark should be worth about a minute. So if you think it's going to take longer than that, leave it, move on, and then come back to it at the end. 3.2. The student used 50 centimeters cubed of hydrochloric acid. Which apparatus would measure 50 centimeters cubed of hydrochloric acid with the greatest accuracy? Okay, so accuracy is all to do with how close it is to the true value. So you've used beakers before, and you'll know that there are graduations on that. So here's an example. Here is a conical flask, and there'll be graduations on the side of that. And then if you think of a measuring cylinder like this, it's got graduations, but they're much smaller. Okay, so it's going to give you a much more accurate reading. So out of these 3, the piece of equipment that will be most accurate is going to be a measuring cylinder. Okay, because even though these 2 can measure volumes, there is a big distance between those graduations. It's not as precise. Right, question 3.3. The student measured the volume of gas produced every 20 seconds for 2 minutes. The volume of gas was 0 at the start of the experiment. So this is very similar to one we did last week, where you might need to put numbers into a table. So we've got the measured volumes of gases. We know that time is what they were doing it every 20 seconds. So time is going to go in our first column, because we always put what we're measuring in the second column. So we're measuring the volume of gas. Okay, now that, if you've got time and volume, that is worth 1 mark. If you've also included the units, which you should always try and remember to do, so seconds for time and centimeters cubed, you can see that here for the volume, then that is going to be our second mark. Now here they've given 0, 0 as the first reading. Sometimes, like the one last week, they didn't give that. So do be aware that at 0 it was 0. So then we need to add the next numbers on here. So it's every 20 seconds. So 20, 40, 60, 80, 100 and 120. So if you got that, that also is worth a mark, just going up in 20s. On the volume side, we just need to plug the numbers in the right order. So the first one is 26, so it goes 26, then 38, 47, 55, 59 and 60, and that's another mark. So 4 easy marks to get on this question. Just remember the units go at the top, don't include them on each number. It needs to go in the top in the title. Right, 3.4. The volumes of gas were lower than expected. Suggest one reason. So remember, with the command word suggest, they're not expecting you to know specifically. They want you to use your common sense. So what could have happened in this practical? That means that the volume of gas was lower than what they thought it would be. So there might be, perhaps, a gas leak. So there might be a leak here that is letting some gas out. So it's not going into the syringe. So that would be a sensible suggestion. It could be that the concentration of hydrochloric acid was lower than what it should have been. They could put that the magnesium was impure, because then you've got less reacting with the hydrochloric acid. You could say that the temperature was lower, or you can say, no, I think that will be all of the answers for that. So the gas leak one could be happening here, so it doesn't matter where you've said it, or up here, either way. Okay, so if it was me, I'd probably say some of the gas could have escaped. Okay, and that's worth 1 mark. So don't overcomplicate the 1 markers. They're expecting just a simple, straightforward answer. 3.5. The student repeated the experiment using different concentrations of hydrochloric acid. Give 2 variables the student should keep the same. So they're changing the concentrations. That is not an answer. That is going to be the independent variable. So what would need to stay the same? Again, there's lots of answers you could give for this that would have an effect. You could say the mass of magnesium. You could say the length of magnesium. Remember, try not to use the word amount. You could say the volume of hydrochloric acid. So even though we're changing the concentration, the volume should stay the same. You could say the temperature. So you could use room temperature each time. So it's going to not have an effect on the investigation. So volume of acid. So any liquids, always volume. Volume of acid. And I'm going to put mass of magnesium. So if you're talking about solids, talk about the mass. If you're talking about liquids or gases, talk about the volume. Right, last question on question 3. Complete the sentences. Now there's 3 spaces and it's worth 3 marks. So we know that even if we go wrong on one of these, we can still pick up marks for the other. As the concentration of hydrochloric acid increased, the rate of reaction increased. Okay, so if you increase concentration, it will make the reaction happen faster. They will accept went up or got bigger, but increased, I imagine, is what most of you have put. Next sentence, this is because there were more acid blank in each cubic centimetre. So the word we are looking for here is particles. Okay, you are allowed to say molecules on that as well, that's absolutely fine, but remember, concentration is the number of particles in an area. So if you have a higher concentration, there are more of those particles in a specific area. And then the last one, so the collisions happen more frequently. Okay, you can say more often, that's allowed as well, but more frequently. So that is a total of 12 marks. So total up how many marks you got out of 12, and make sure you make a note of any that you did not get right, because that is what you need to make sure you revise. Right, question 4. This one is looking at hydrocarbons and the crude oil topic. So large hydrocarbon molecules can be cracked to produce smaller, more useful molecules. Alkanes and alkenes are produced when hydrocarbons are cracked. Again, we've got an example where they're giving you this information, but you don't need any of that to answer this question. It's just asking what are the 2 conditions needed for cracking. Now, most of you, I imagine, have put high temperature. Don't just put temperature, it needs to be high temperature. And then some of you might have put steam. I'm going to put catalysts. Okay, so you can have high temperature, catalyst, a steam. Something else you might have put is high pressure or low oxygen, but high temperature, catalyst and steam I think are going to be the most common answers. So you get 1 mark for each of those, and that is a total of 2 marks. 4.2, butane, which is C4H10, is an alkane. Figure 5 shows the displayed formula of butane. Complete the structural formula of butane. So it's giving you information here, so we know that there's got to be 4 carbons. At the moment we've only got 2, so we can start by adding the other 2 carbons. We've got 1, 2, 3, 4, 5 hydrogens, but we need 10. So we can add our hydrogens to our picture. Remember, each carbon has to have 4 lines coming off it. So each carbon makes 4 bonds. Got 1 there, 2, 3, 4. That will be what it looks like for butane. Now, even though it gave you the information about butane, you are expected to know that methane contains 1 carbon, ethane is 2, propane is 3, and butane is 4. So they have given you the information in the question this time, but you are expected to know those first 4. Right, 4.3, butane burns in oxygen. Complete the word equation for the complete combustion of butane. So as this is complete combustion, we will not have any carbon monoxide or pure carbon. So whenever a fuel, such as butane, completely combusts with oxygen, it's going to form 2 things. You're going to form carbon dioxide and water. Okay, when we burn the fuel from our food inside us, we produce carbon dioxide and water as well. So it's the same as respiration, but in respiration the fuel is glucose. So you're going to get 1 mark for carbon dioxide. Most people get carbon dioxide. Very well done if you got water as well. That would be your 2nd mark. Okay, 4.4, ethene is an alkene. Give a test for alkenes. Give the result of the test if an alkene is present. So for the test we need to say what it is that we're going to use. And to test for alkenes we use bromine or bromine water. Okay, so that is that orangey liquid that we can add to it. Give it a shake, and if it is an alkene, the result is it goes colourless. Do not put goes clear. Clear and colourless are 2 different things. You can have clear blue liquid like copper sulfate because you can see through it. That's the clear. Colourless means that you lose that colour. So you get 1 mark for knowing bromine water, and you get 1 mark for saying it goes colourless. So that is 2 marks. Right, last question on question 4. Each year, many tons of crude oil are extracted from the earth. It took millions of years for the crude oil to be formed. What do we call development? what do we call development that meets the needs of current generations without compromising the resources for future generations? It's quite a mouthful, that sentence. So what is it where we don't use more than what we need, so there is enough for future generations? Even though crude oil is a finite resource, that's not what it is asking. It's asking for sustainable development. So sustainable development means that you're not using more, so it means that future generations will have enough themselves. So that's worth 1 mark for the 1 box. So if you total that up out of 8 and make a note of any sections that you didn't get right so that you can revise that. Right, question number 5. So figure 6 shows the percentage by mass of some metals in the Earth's crust. So we've got the percentage going on the y-axis and then the different metals on the x-axis. And we can see that magnesium's not in, so it's probably going to ask us to do that later on. What is the percentage by mass of calcium in the Earth's crust? 1 mark. So it's asking us to be able to read from a graph using the scale to work out a percentage. So here is our calcium bar. So it's going up to here. It is halfway between 2 boxes. So it is here. So it's dead between 3 and 4. So the answer for that is going to be 3.50. Okay. If needs be, perhaps use a ruler. Put the ruler at the top, make a mark. Remember, you can draw on these graphs. It is not going to get you marked down. And then take the reading from that. 5.2. The percentage by mass of magnesium in the Earth's crust is 2.1. Draw the bar for magnesium on figure 6. So here is where we're adding our bar to the graph. So the first thing we need to do is work out the scale. So here is 0, here is 1. And there are 5 little boxes. So that means that every little box is going to be worth 0.2. Okay, so 0.24681. So we've got to get to 2.1. So here is 2. That would be 2.2. So 2.1 is going to be halfway between the 2 and the 2.2. So using my ruler, I'm going to take that and I'm going to just make a little mark here where that 2.2 is. Okay. Now how wide you do your bar is technically important, but you wouldn't get marked down in this question. So they've got 2 little boxes on either side, left's free, so I'm going to go 2 little boxes to here, and then 2 little boxes up as well. There we go. What they are going to be looking at is that this line is halfway between, is in between those 2 boxes. Okay, so please try and be as accurate as you can on these questions. And that is worth 1 mark. 5.3. Copper sulfate is produced during the extraction of copper from the Earth's crust. Copper is produced from copper sulfate solution using iron. The word equation for the reaction is copper sulfate plus iron makes iron sulfate plus copper. From the equation, a company calculated that 648 kilograms of copper sulfate are needed to produce 617 kilograms of iron sulfate and 258 kilograms of copper. Calculate the mass of iron needed to make 258 kilograms of copper. So they want to know how much of this will make 258 kilograms of that. Okay. Now it's given us in the information, it's given us that 258 kilograms of copper uses 648 kilograms of copper sulfate. So we can start putting in the numbers that we know, 648. So there's 648 kilograms of copper sulfate reacting with an unknown amount of iron, and that's going to make iron sulfate which is 617, and 258 kilograms of copper. In a reaction, whatever goes into the reaction must come out. Okay, that is conservation of mass. So if we add these two numbers together, so I just use my calculator. So 617 plus 258, that gives me 875. Now if you write 875 or 617 plus 258, they give you a mark. Okay, so the total is 875. So this has to be 875. So we need to take that 648 from 875. So 648. So I'm popping into my calculator 875 minus 648, and that gives me 227. So if you got 227, that is also a mark. Okay. If you put 227 without the working out, that is automatically worth 2 marks, but as we always say, please show your working out, because if you get this bit wrong, you can still pick up marks in the working out. Right, 5.4. Copper is a catalyst, is used as a catalyst. Figure 7 shows the reaction profile for a reaction without a catalyst. Draw an arrow on figure 7 to show the activation energy. Now sometimes they can be pretty picky on this, so we know that this bit is the activation energy. That's the amount of energy needed to start the reaction, so that's the bump. So what you want to do is, using a ruler, draw a line. So I'm going to do a little dashed line going across. Okay, and then from the top of the peak, it's going to be the maximum amount. I'm just going to draw my arrow. Okay, so this is showing the activation energy. If you put one there as well, then that's absolutely fine. Okay, but we need to have it from the bottom of this line to the very top of the curve. So that is worth 1 mark. 5.5. The reaction profile for the reaction without a catalyst is shown again in figure 8. So we've got the same graph again. Draw a reaction profile on figure 8 for the same reaction with a catalyst. Now we know that catalysts reduce the amount of activation energy needed. So it gives a different pathway for the reaction, which requires less activation energy. So this curve up here needs to be lower down. Okay, so it's going to go from the same point, but I'm just going to do a curve that is below this curve. It does not matter where you've put this curve as long as it is below this one and obviously above the line. And that is worth 2 marks, because it wants you to know that the activation is less and that we show that with a lower curve. So that's 2 marks. Right, the last part of the question. What are catalysts in biological systems called? Now I hope that everyone has got this one, because we've said it many, many times. Biological catalysts, so bio means living. So the ones that living things produce are called enzymes. Okay. Now enzymes are used in detergents, but we don't produce detergents. It's polymers is where things are joined together, where you have the monomers joined together to make a poly. Poly means many. Solvents are things that dissolve solutes. So even if you were doing it by elimination, hopefully you got to enzymes as well. So total up the number of marks from that question and make a note of anything that you need to revise. Okay, question number 6. Water that is safe to drink contains dissolved substances. What do we call water that is safe to drink? I hope that we have all ticked potable water. So the stuff that comes out of your taps, that is potable water, is safe to drink, but there are things that are dissolved in it. Desalination, that's taking seawater and removing the salt. Filtering is just where you take out the solids, but there could be, say, bacteria and things like that. And fresh water, that's just coming out of a spring or something like that. So I'm sure most of you got potable water. 6.2, describe a test for pure water. Give the result of the test if the water is pure. So this kind of is set out like one of the gas tests, but this isn't in the chemical analysis gas test section. So what do we know about pure water that is specific to pure water? We know that it boils at a specific temperature. We know that that temperature is 100 degrees Celsius. So to test it, we can boil it. Okay. They will not accept heating, because you could heat it and it would just get to 40 degrees Celsius, which wouldn't be enough to boil it. So we do need to say something about boiling the water. The result is that it will boil at 100 degrees Celsius. So if we've got those two things, that's 2 marks. So you get 1 mark for boiling and 1 mark about 100 degrees Celsius. Okay, 6.3. So this question is worth 4 marks. Describe a method to determine the mass of dissolved solids in a 100 centimetre cubed sample of river water. So I think this is one of the first practicals that I filmed and put on the YouTube channel. This is a required practical, so we do need to know how to do this. So first thing that we can do is measure 100 centimetres cubed of water, of river water or sample. Okay. Now, when we did the practical, we used an evaporating dish, and we weighed the evaporating dish before we did anything with it. So it wouldn't matter if these two are actually the other way around. So weigh evaporating dish. Okay, so that's going to be the first steps, and as I say, it doesn't matter which way round those two are. We're then going to put the sample into the dish, and then as the name suggests, we are going to let the water evaporate. So you could say leave the water to evaporate, that's fine, or you might have said to heat it, so water evaporates. Something about the water evaporating is what is important there. Then once all the water's gone, we're just going to be left with those dissolved solids. So we need to weigh the evaporating dish again. Okay, so that's going to tell us the mass of the evaporating dish and the solid. So to find out the amount of solid, we just need to take off the original evaporating dish. So you can just say, you can give the calculation, or you can just say calculate mass of solids. Okay, so I would say that if you have got one of those steps, then that's going to be worth 1 mark. If you've got a couple of them, so I'd say 2 or 3, that's going to be worth 2 marks. If you have got 4 of them, then I'd probably go 3 marks. And if you've got all of them, or you're just missing one of them, then that would be your full 4 marks. Okay, does need to be in a logical sequence to be in the top marks, so 3 to 4 marks. You are free to bullet point if you're asked to do a method, so don't write it out like an English essay or anything like that, just short and concise. Okay, next one, 6.4. A sample of river water contains 125 milligrams per decimeter cubed of dissolved solids. Calculate the mass of dissolved solids in grams in 250 centimeters cubed of this sample of river water, and give your answer to two significant figures. Right, so this is worth 4 marks. So if you're asked to do any calculations, look at the number of marks it's worth. This is 4, so there's going to be several things that you have to do. And I've actually underlined one of the things that stood out as I was reading it, is that you've got 2 different units here. Okay, now 1 decimeter cubed is 1,000 centimeters cubed, okay, or a litre. So 1,000 centimeters cubed is a litre. So 1 decimeter cubed is 1,000 centimeters cubed. So 250 centimeters cubed would be, if you divide that by 1,000, so 250 centimeters cubed divided by 1,000 is 0.25 decimeters cubed, or a quarter of a decimeter cubed. Now if you have got that conversion, that is worth a mark. Okay, now there is also an issue with the grams. This is milligrams and this is grams, so we need to convert the milligrams into grams. So again, to do that, there is 1,000 milligrams in a gram, so 125 milligrams is 0.125 grams. Okay, if you're really unsure about conversions, most of the time it's 1,000, so you're either going to have to divide or times by 1,000. A milligram is smaller, so you can have more of them in a gram. Okay, so I always used to go back, just check that it made sense. Now that conversion is also worth 1 mark. So now we're going to move on to the calculation. So there is 0.125 grams for every 1,000 centimeters cubed. So to work out for 250 centimeters cubed, we need to do 0.125 times 0.25. Okay, now if you have got these conversions wrong, but you have times them together, you still get a mark. Okay, you can't be marked down twice for one mistake. Now that will give you an answer, if you pop it into the calculator, of 0.03125. Okay, now it's asking for 2 significant figures. 0 is not a significant figure. 0 again, not a significant figure. So we need it with these 2 numbers. So I look at this one, that's a 2, so I'm going to keep it as 3, 1. If it was a 5 or more, obviously you would have to round it up. So the final answer is 0.031, or doing that conversion to 2 significant figures gets you that mark. So even if you got the wrong calculation but you converted to 2 significant figures, you would still get the mark. So the last bit for question 6. A water company allows a maximum of 500 milligrams per decimeter cubed of sulfate ions in drinking water. A sample of drinking water contains 44 milligrams per decimeter cubed of sulfate ions. Calculate the percentage of the maximum allowed mass of sulfate ions in the sample of drinking water. So if that is what the sample has, and that is the maximum, it's saying calculate the percentage of the maximum. So it's going to be what we have, 44, divided by 500, and then you're going to multiply that by 100 to get it into a percentage. If you've written that, then that will be worth a mark. So even if the final answer is wrong, that will be worth a mark. Now if you pop that into your calculator, that gets you 8.8%. So 8.8% is your second mark. You could have rounded it to 9, Now this question was quite a tricky question, as in all of the questions for question number 6, especially as there's those 2 4 markers. Something that is very important to remember is that conversion. So 1 decimeter cubed is 1,000 centimeters cubed. Okay, so if you're unsure of that before, please make sure that you remember that in the future. It's out of 13, so if you go through, give yourself a total out of 13 and make a note of anything that you need to revise further. Alright, well done guys, we've made it to the last question, question number 7. So this question is about atmospheric pollutants from fuels. Fuel burns in a car engine. Describe how oxides of nitrogen are produced in a car engine. So we know that this happens in a car engine because car engines are really hot. So if you have said something about there being high temperatures in the engine, or worse, that affects, then that is going to be 1 mark. So you need those high temperatures that the engine provides to actually cause the reaction. And what's actually happening is the oxygen and nitrogen just in the air are being forced together, being bonded together. So high temperatures, and then we need to say oxygen and nitrogen react. Okay, and that's going to be the 2nd mark. So because the engine is very, very hot, it causes the oxygen and the nitrogen to react. Instead of saying react, you can say bond, or you can say combine. That also is accepted on the mark scheme. So that's worth 2 marks. So we're on to the very last section, and it is a 6 marker, everyone's favourite. Please do not be put off by these. It's very easy to pick up marks if you know what you're doing. So 7.2. Table 3 shows the carbon footprint during the manufacture and use of 3 cars. So it gives you an information. You've got your 3 cars, you've got the massive CO2 when it's being made, manufacturing, when driving, produces from manufacture and 40,000 kilometers of driving, and the total mass for 100,000 kilometers and the manufacturing. Now if you see a big table of information, even though it looks scary, it's actually easier because you just need to refer to the information that is in there. So let's have a look at the question. It says evaluate the carbon footprint of the cars. Now the command word here is evaluate. Now if you're asked to evaluate anything, we've got to give advantages or good things or benefits, and we need to say the bad stuff as well, so disadvantages, and then at the end we make a conclusion of what we think is best. So it's asking us to kind of look at the good and the bad of these 3 different cars and then give an idea of which one we think is best. So we've got all the information here. So there's a few things that we can talk about. So we could say, for instance, looking at the table, if we go through each column, so we can say that car A produces the least amount of carbon dioxide. Okay, that would be a relevant point when being manufactured. We could say that car C produces the least amount of carbon dioxide every kilometre. We can say that if we put these together for 40,000 kilometres, that car A produces the least amount of carbon dioxide, and also at 100,000 kilometres per kilogram of carbon dioxide. So I'm going to pop on here the actual mark scheme. I'm going to go through some of the statements that you might have made. So I'm going to move this down a bit. There we go. Across. So we've got some examples of relevant points. So if you are making one or a couple of these relevant points, then you are going to be in the first level. Okay, so I'd say if you've made 2 points about it, it's going to be worth 1 mark. If you've done 3, then that's going to be worth 2 marks. So if you said that car C produces the most carbon dioxide at manufacture, or you've said that car A produces the least, either one of those, then that is a relevant point. If you said that car A produces the most carbon dioxide per kilometre, then that is a relevant point. If you said that car C produces the most carbon dioxide after manufacture and driving, and B produces the most after 100,000, or A produces the least, then all of those are examples of relevant points. So I imagine that most people have put a couple, at least 2 relevant points in their answers. So that gets you to the first level. Level 1, relevant points are made. Okay, and that'd be worth 1 to 2 marks. To get to level 2, we've got to give a couple of logically linked reasons. So if we say that, for instance, car A produces the least amount of carbon dioxide during manufacture, but most carbon dioxide per kilometre instead of just writing it out line by line, then that is a logically linked answer. You might have said that car C produces most carbon dioxide during manufacture, but the least amount per kilometre, then that is a linked response. Car A produces least carbon dioxide during manufacture, but car C produces the least carbon dioxide per kilometre. So you're comparing the different cars. All of those are examples, not all of them, but those are examples of some linked statements. So if you have put 2 linked statements in there, then you're going to be in level 2. So I'd say if you've got 1 linked statement, then that's going to be worth 3 marks. And if you've got 2 or more, then that's going to be worth 4. And to get the top grade, we need to have linked statements and also said which one we think is best and why. So if you have got several of these, so if you've got 2 or 3 of these, and you have said which one overall is best, such as overall car A has the smallest carbon footprint, as it has the smallest CO2 production in manufacture and the smallest mass of carbon dioxide after 40,000, then that is your judgment because you've said which one you think is best and why. Okay, or you might have said car A eventually will have the largest carbon footprint because it produces more carbon dioxide, so it would be better to get car B or C. Okay, so that is a thought out justification, and if you've got that, then that is going to be 5 or 6 marks. So give yourself a mark out of 8 for that, so that's the 6 marks on this and the 2 previous ones. As I say, if you are given a table, please just look at the information, look at the command word, what's it asking me to do. If I'm evaluating it, I need to say the good and the bad, which one's best, and why. So that's it from me. On Thursday, obviously, you'll be back in lessons, so I will see you then, or see you at testing. Take care of yourselves and goodbye.